So here we go. We're going to talk about rational functions. Okay, we've been graphing polynomials. Now we're going to graph some rational functions. Okay, so more graphing. Yay. All right. You guys get in. Let's get my joke up here. What's true about decimals of irrational numbers? They go on and on and on and they don't repeat. Okay? Like rational numbers, if they have decimals that go on forever. Anyway, math joke. Moving on. Okay, so a rational function is a function that can be written as a fraction where we have a polynomial in the numerator and a polynomial in the denominator. Okay? Our numerator and denominator cannot have any common factors. If they do, we must cancel them out. If our numerator and denominator have common factors, we have to cancel them out. Okay. Okay. Now we've kind of worked with domain already with rational functions. Okay, when we talk about the domain of a rational function, we are worried about what? Where our denominator is 0. Okay, we cannot divide by 0. So when we look at the domain of our function, we look at where the denominator is 0, and we know that we have to exclude those from our domain. What are some characteristics of a rational function? Okay, you graphed these last year in Algebra 2. What do they have? When the denominator is 0, what does that cause graphically to happen?
Undefined.
Okay, and what does undefined look like graphically? A vertical line, right? Okay. So when we have a denominator, okay, when we have a denominator that is 0, okay, or wherever the denominator is 0, it is creating a vertical asymptote in our graph. Okay. So what is a vertical asymptote, first of all? Okay, a vertical asymptote is a line, x equals a, where on either side of this line, we're either going to approach infinity or approach negative infinity, but we're not going to cross the vertical asymptote. So as we get closer to the asymptote, we're either going to go up and up and up towards infinity, getting closer and closer to the asymptote, or down towards negative infinity, getting closer to the asymptote. Okay? Vertical asymptotes occur when our denominator is 0. What other characteristic does a rational graph have? It could have a vertical asymptote, or 2, or 3, if we're really crazy. But it has some vertical asymptotes. What else can it have? Are there any other kinds of asymptotes? Or do we only have vertical asymptotes?
Horizontal.
We have horizontal asymptotes. Okay, what is a horizontal asymptote? Same kind of thing, right? Except we're going horizontally. Okay, so a horizontal asymptote is a horizontal line. We're going to graph it as a dotted line where our graph is going to approach that line as we go towards infinity and negative infinity. Okay, so you might remember it looking like, I don't have a lot of room. So like our reciprocal function, we have a vertical asymptote, a horizontal asymptote, and towards infinity, our graph is going to approach that horizontal asymptote. Something that, yes. Okay, that's what I'm about to talk about, okay? Something that we need to discuss, a horizontal asymptote is defined by the ending behavior. As we go to infinity, our graph is going to approach that line. As we go to negative infinity, our graph is going to approach that line. It is okay if our graph crosses the horizontal asymptote kind of more in the middle of our graph, as long as towards the infinities we approach the line. Okay, so we are going to get some graphs that cross the horizontal asymptote, and that is allowed. Okay, because the definition of a horizontal asymptote is that towards the infinities will approach it. It's okay to cross it in the middle. Okay, now let's talk about our rules for horizontal asymptotes. Okay, do you remember what happens when the degree of our numerator is smaller than the degree of our denominator? We have a horizontal asymptote where? Not remembering? That's okay. If the degree of our numerator is smaller than the degree of our denominator, then y equals 0 is our horizontal asymptote. If the degree of our numerator is smaller than the degree of our denominator, then we have a horizontal asymptote at y equals 0. What about when the degrees are the same for numerator and denominator? Do you remember that? Not going back to any of this? Okay. When the degrees are the same, then we look at the ratio of the leading coefficients. Okay. We have a horizontal asymptote at y equals whatever the ratio of the leading coefficients are. Okay. And we will do an example of each one of these so we know what's going on. Okay. And then last, if the degree of the numerator is bigger, we actually do not have a horizontal asymptote. We have what is called a slant asymptote. Okay? This is something that in Algebra 2 you skipped over. Here in pre-calculus, we get to see what's happening. Okay? So you need to remember these 3 rules. At one point, you did know these 3 rules. Hopefully, they can come back to you quickly. Okay. okay? But it's important that you are able to identify a horizontal asymptote. Okay, so we're going to do 3 examples, one of each kind, okay? But before we get to the examples, I want to talk about the process you should take to graph these, okay? So the first thing I said was that your function needs to be simplified, okay? So, simplify f if possible, okay, which probably means you're going to need to factor both the numerator and denominator, all right, to see if anything can cancel, okay? The next thing you're going to do is you're going to identify all of your asymptotes. Where are your vertical asymptotes? Put them on your graph. Where are your horizontal asymptotes? Put them on your graph. That way you kind of have an idea of what x values you need to pick to create your curve. Okay. When you sketch the curve, okay, x and y intercepts are nice values to find. Okay. And then you're going to have to do some plugging in numbers, making little XY tables to figure out your points. Your vertical asymptotes are going to break your graph up into chunks. Okay, so each chunk of the graph, I need at least 2 points so you can get a general shape. Okay. Once you have enough points so you know what is going on, you can connect your points with a smooth curve, a lot like polynomials, right? We have to be nice and smooth. And then with our knowledge of our asymptotes, we know what our curve should approach. All right, are you ready? Okay, like I said, we're going to do I guess we are going to do 3 examples, but it's not necessarily one of each type, okay? There is something special that happens if we get things, if we get factors to cancel, so that's more of my second example. Okay. Okay, are you ready? All right, here is our first example. Okay, for each of these, we will talk about obviously the asymptotes and the graph and whatnot, but we will identify the domain and range for each of these. Okay. So 2x squared over x squared minus 1. The first thing we have to do is simplify. So no matter what, we're going to factor both the numerator and denominator. So our numerator, we're going to leave as 2x squared, but we're going to rewrite our denominator as what? X minus 1, x plus 1. Okay. Is this simplified? Yes, nothing can cancel. So let's look at vertical asymptotes. What values would make our denominator 0? 1 and negative 1. So we have vertical asymptotes at x equals 1 and x equals negative 1. Since those 2 values make our denominator 0, we know that they cannot be in our domain. So if we were to describe the domain, we know we have everything before negative 1, in between negative 1 and 1, and after 1. But we cannot include negative 1 and 1 in our domain. All right. Where would our horizontal asymptote be? Okay, what's true about the degrees of the numerator and denominator? Same, are they? They are the same, which means we look at the ratio of the leading coefficient. What's the ratio of the leading coefficient? 2/1. So our horizontal asymptote is at 2. All right, now we want to identify the range, but with these graphs, I don't want you to do that until after you have graphed it. Okay, so we will come back and look at the range once we have graphed it, because some funky things can happen. All right, so let's talk about what we know. We know that we have a horizontal asymptote at 1 and -1. Up here on my graph, so I have enough room for you to see, I'm going to count by halves. Is that okay? Is that okay with everyone? Okay. So we have x is 1, x is -1, and y equals 2. Okay. Now we can just make an XY chart. Okay. First of all, in my opinion, the easiest thing to do is go to your asymptotes and go on either side of the asymptote. So we have an asymptote here at 1. So the next nice number to plug in would be 2. Well, we'll go to the right way. So 2 would be a nice number, right? What do we get when we plug in 2 for x? I would go back to the original one right here. 8/3. And we'll plug in another one. 3 would be nice to plug in. What do we get when we plug in 3? Wouldn't it be 18/8? Okay, which I'm going to simplify to 9/4. Is that all right? So at 2, we're at 8/3, and at 3, we're at 9/4. There's that curve. All right. Let's go way over here on the left side of -1. Nice numbers to plug in are -2 and -3. What happens when we plug in -2? We get 8/3. What happens when we plug in -3? We get 9/4. That is kind of nice, isn't it? Okay, now we have to figure out what's going on in between these asymptotes. I will tell you right now, if you have 2 vertical asymptotes, one of 2 things is going to happen. Either your curve is going to snake through the middle and go through the asymptote, or you're going to have more of a U opening either up or down. So we need to figure out what's going on. Okay, so an easy point for us to pick would be the y-intercept. What happens when x is 0? What do we get for y? 0, right? Okay. Now we have to figure out what's going on either side of 0. So unfortunately, we are going to have to plug in 1/2 and -1/2. Okay. Pods 1, 2, and 3 plug in 1/2. Pods 5 and 6 plug in -1/2. When you get something, let me know. What? I heard a value. Negative what?
Negative 2 number for negative 1/2.
Negative 2/3.
2 1/3 or 7 I don't know.
Okay, what's 1/2 squared? 1/4 times 2. So we have 1/2 over 1/2 squared is minus 1. Negative 3/4. So we have 1/2 times negative 4/3, which reduces to what? Negative 2/3. That happens for both of them. Okay. So are we getting a U or a SMIC? Getting a U. Okay. So now let's talk about our range. Where is our range? Okay, where do we have values? Negative infinity, and they stop at 0, right? Do we include 0?
Yeah.
And then where else do we have values? We have them above our horizontal asymptote, so 2 to infinity. Lots your asymptotes, find values in between. Your points are not always going to be nice. You're going to probably be dealing with some fractions.
What about the left of the vertical? We include those values.
What do you mean, like your domain? We've already identified the domain.
Oh, my bad.
Yeah. Okay. Let's look at this one. This is where it gets interesting and fun. All right. This is a pre-calculus example, not an algebra 2 example. Okay. What's the first thing we have to do? Simplify. What does our numerator factor to? Good. What's happening? What does our denominator factor to? X minus 3 times. Aha! So what happens?
Reduced.
We can reduce to x minus 1 over x minus 3. Okay? Now, what is happening right here? Okay? X plus 2 canceled out, which means in our graph, we have a hole at x equals negative 2. We do not have a vertical asymptote. We have a hole because those factors cancel. Okay? It's still an undefined value because it makes our original denominator 0, but since we have factors that are canceling, we have a hole. Okay? And I'll show you what that is going to look like. So we are now working with this. Okay? We have this graph with a hole. So where is our vertical asymptote?
3.
X equals 3, correct? Because that's where our denominator is 0.
Oh,
Okay. So our domain, we have a vertical asymptote at 3. Negative 2 is still making our denominator undefined, our denominator 0. So when we identify the domain, we have to exclude both numbers, -2 and 3, since both of those values are making our denominator 0. Where is our horizontal asymptote? Y equals 1. Right? Because we have the same degree, so we look at the ratio of the coefficients. All right, so now we're going to graph it. We have a horizontal asymptote at x equals 3. I'm sorry, a vertical asymptote at x equals 3. And a horizontal asymptote at y equals 1. Okay, let's go to the right of our asymptote. What would be a nice number to plug in? 4. And we can go to the reduced version. It's nice and easy to plug in there. What happens when we plug in 4 to the reduced version?
3.
We get 3. And then we should probably plug in 5. 5 would be nice, right? What happens when we plug in 5? Oh, these are nice numbers, aren't they? So we get this nice curve here.
Is there not a curve on the sides of the asymptotes?
It will always curve like that, whether it be above or below. Okay. All right, let's look on the other side of our asymptote. What would be a good number to plug in? 2. And what happens when we plug in 2 to the reduced?
Negative.
We get -1. And then what's another value we should pick? 0. And what happens when we... Oh, okay. 0. What happens when we plug in 0? We get 1/3. Okay, so there's our y-intercept, right? Okay. Now, let's go back. Since we had factors that cancel, that means we have a hole at x is -2. So when I plug in -2 to our reduced function, what do we get? Positive 3/5. So here at -2 3/5, we have a hole in the graph. Okay. So this graph looks the same as x minus 1 over x minus 3, but there's a hole there. That's the difference. Okay. So let's talk about what our range is. Where do we have y values? We have values from -infinity until okay, we have 2 things to worry about. Do we have a value here? No. So 3/5 is not in our domain because of the, or in our range because of our hole. What else is not in our range? 1 because of the asymptote. Okay. If your factors cancel, you have a hole. You will have at least 2 problems in your homework with holes. Okay, so beware. Okay. All right, let's talk about the slant asymptote. Okay, this is where it's really exciting. Okay, are there any questions on the hole before we go on? Okay. So we get a slant asymptote if the degree is exactly 1 higher than the denominator. The numerator is exactly 1 higher than the degree of the denominator. That's all you're going to see right now in this class. Okay. So to find the equation of our slant asymptote, we're actually going to perform division of the numerator to denominator, okay? We have a big fraction. If the degree of our numerator is larger, that means we have an improper fraction and we can divide. So to find the slant asymptote, we're actually going to perform the division, and the slant asymptote will be the quotient of the division. We don't have to worry about the remainder. There probably will be a remainder, but we don't really care about it. We're just worried about the quotient portion of the division. Okay, so everything's going to be the same except when we identify the horizontal asymptote, there's not one, it's slant, and then we have to find it. One nice thing is I will not make you identify the range on a function with a slant asymptote. Okay, because it's too messy. I will come back to this if you need to continue writing it down, but I want to get to our example, okay? Okay, so here's our example. What's the first thing I tell you to do? Okay, factor just in case we can reduce. So how would we write the numerator? Okay, and our denominator is x plus 1. Okay. Where is our vertical asymptote? X equals -1. If you write -1 on your quiz Friday, I will not give you credit. It's a line, x equals -1. Okay? Which means our domain is everything except -1. Okay? Now, the degree of our numerator is greater than the degree of our denominator, so we are going to have a slant asymptote. Okay? So let's talk about finding the slant asymptote. Okay? We are actually going to perform the division of our fraction. So, would you like to use synthetic or long division? Synthetic division, we have a linear denominator. Let's use synthetic division. Okay? So we have x squared minus x plus 0. And we are going to divide it by x plus 1. So what are we going to put out here? -1. Okay. So when we perform the division, we drop the 1. 1 times -1 is -1. Add to get -2. Multiply to 2. Okay. The remainder, don't even find it because it doesn't matter. What this is saying is that our slant asymptote is y equals x minus 2. Okay. Whatever your quotient is, forgetting about the remainder, that is your slant asymptote. Okay? So instead of a horizontal asymptote, we have this line. So how do we graph this line? Y equals x minus 2. We go to our y-intercept of -2, and we have a slope of 1. Okay. From here, we can just pick points. Pick a couple on either side of your asymptote. So since our asymptote's at -1, let's pick 0. What do we get when we plug 0 into our function?
Oh, right there.
Our function.
-1.
0, right? So 0 squared minus 0 in the numerator. What happens when we plug 1 into our function? 0. Okay, that's kind of strange. But we know what's supposed to happen. So we know that it's supposed to approach the slant asymptote and the horizontal asymptote, or vertical asymptote, excuse me. That looks worse. Here we go. All right, on the other side of -1, what happens when we plug in -2?
-6.
-6. What happens when we plug in -3? Okay. We should have some symmetry in these graphs. Do you agree? So there's our graph. Can you see why I don't want you to worry about the rings? Oh my goodness. There's your homework. Wednesday always robs us of a few minutes. I apologize. Okay, those first few are matching, and then you have 1, 2, 3, 4, 5, 6, 7 graphs. Tomorrow we will spend more time on graphs.
I'm like, something's off because I do have to.